ولا؟
Hi, everybody. Good morning, good afternoon, and good evening, wherever you are or whenever you might be watching this. I'm honored to welcome you to today's session. Today, I'm hosting Dr. Khaled again, and today we will talk about, or we will pave the road to word-to-vector algorithm. So, Dr. Khaled, welcome again, and you have the floor.
Thank you, Dr. Salem, for the nice introduction. And let's get started. We will do a recap of what we have covered in the previous two lectures. We've covered that the rate of change is one of the most important and critical concepts in machine learning. And we said that the rate of change, machine learning is the rate of change. And the rate of change took us into the concept of instantaneous rate of change, where the interval gets smaller and smaller and smaller and smaller until it gets zero. And that took us to the concept of first derivative. And from first derivative, we jumped into the idea and the concept of partial derivatives. And partial derivatives are nothing but same as derivatives in two dimensions when we fix all the variables in the function except for one variable. And we have shown that partial derivatives are not really as scary as we thought them. And then we talked about the loss function and how the loss function quantifies the prediction or the difference between the prediction and the actual value, and how minimizing a loss function will find our machine learning model. So we talked about the rate of change a lot, and that will change. From now on, we will not mention the rate of change that much, because at this point, we have passed the point where we need to understand the rate of change. So if you feel that you need to review the concepts that we covered in the previous lecture, like the rate of change, or if you feel nostalgic to the rate of change, you can go back to our first two lectures in the series, and here we have put their links. Generative AI, as we all know it, and a good example is ChatGPT, where you prompt it and give it text, and it will generate a response, either video or image or a text. We need to understand how it understands the human language. How does these models understand the language that we speak? Look at this example. It's a text prompt where I am, or where we are, asking a ChatGPT about visiting Portland, Oregon. And I have lived in Portland, Oregon for about 3 years and 8 months. And actually, it gave us correct information. It says that we should visit Portland, Oregon from May to June and early September. And that's where the weather is nice and you see sunny days, because all the days of the year other than this period is actually just gloomy and rainy. So ChatGPT understood our question and it responded accurately. It's like maybe ChatGPT lived in Portland, Oregon. You never know, right? So in order to understand how ChatGPT and similar websites and technologies understand our natural language, we need to understand two concepts: tokenization and word-to-vector. So before the text or our prompts go into or enter the ChatGPT, a word first gets divided or broken into tokens, and some words do not get broken into tokens, and these tokens will be transformed in something called vector that we will cover. And these mathematical notation.
Dr. Khaled, why
Yes.
they call it token? Why just call it something else, like a word or whatever, a part of the word?
So that's a good question that will be covered in the later slides, because a word is a unit of a human language. Are there any other parts of the word that can convey meaning? So that's the intuition of tokens for us to understand what is tokenization, like psychology, for example, or disrespect. It's clear that it's divided into two parts. We will talk about this in a little bit more detail in the next slides. Now, we said that computers do not understand the language that we speak. If I said summer in Portland is beautiful, computer will not understand summer or rain or whatever. Computer understands only zeros and ones. Computer understand numbers. So how do computer understand natural language? This is what we hope to provide a level of understanding in this lecture. So, Dr. Salem, you have the floor here.
This letter code is a code that the computer should understand, right?
Yes, yes. I mean, you're right. You're saying that each code has an each character or each letter has an identifier.
Right. So even though still the computer couldn't understand this code, right?
Yes, right. I mean, if we give it to the computer, it might. Let's see. So the word base, for example, you say and when we're discussing, for example, you can say why not represent each letter in its identifier or in its ASCII code and give it to the computer, right? So if you look here, this
Is
text to the
that
left.
is that enough?
Well, let's see. Let's see. That's a good question. That's one of the questions we want to answer in the slides. Here in the left image, we have seen that actually the statement, Portland in summer is beautiful. We have represented that in numbers, where each letter is transformed to its number. And to understand an analogy of this, suppose, can you read, Salim, this text here?
Ugun, Nasil, Sin, Imi, Yasin. Yeah.
I mean, I know some Turkish, so I would say
Yeah.
that your pronunciation is not bad, but can you understand it?
No.
This is how computer sees a flow of characters or a flow of letters. It can understand each character as we are able to pronounce each character separately, but it cannot understand the meaning. So, is there a better way to present the human language, or they call it the natural language, to the computer? That's what we're gonna see. And by the way, this means today, how are you? The guy who wears a green shirt says, I am good, and you. Well, maybe. I
Mm.
mean, I'm not, my Turkish is not that great, so don't take it to the T. Don't rely it. Okay, we can look it up after the lecture and see what it means. So to understand how the computer understands, we need to understand what a vector is. If you want to add anything, Salim, here you have a questions. Feel free to comment.
No, that's fine.
Good. So we can think of a vector as a record in a database. If you are a software developer, you are familiar with the database tables, or even you don't have to be even a computer developer to understand what a vector is. A vector, if you have an Excel sheet where you are, for example, recording your employee data, their salaries, their remaining vacation days, the number of patents, or the number of mistakes you've done. Some program managers do that anyway. So you can represent that as a vector where you put all these together. So really, it's not
So
that difficult.
this is the table on the left, and you transfer it to vector.
Yes, exactly. You took some numerical attributes and put it as a vector.
And these three elements in this vector represent the age, salary, and patients
Patents, number of patents.
or patents.
Yes. And yes,
What
now we
what
need,
what about the employee? There is no representation for that.
well, that's a text. That's a
Oh, I
text.
see.
So we need to somehow to put it in a vector, we need to transform it in a numerical form.
I see.
But for example, here the attributes or the characteristics we care about, we can put them in a vector and we can draw conclusions.
I
But
see.
that's yeah. So why do we care about a vector? What is very specific about a vector? A vector
Because
has
of the
two important,
operations on the vectors?
the what? Sorry.
Because you can do the operations on the vectors.
We can do operations on the vector, but before we do operations on the vector, we need to understand what are the most two important features or qualities of a vector, which is direction
Okay.
and a length. So what do we mean by, feel free, Dr. Salim, to make any comment
No,
anytime
that's
or
fine.
interrupt me if I'm going too fast, okay?
You're
Uh,
good.
so the length of the vector is one of the features. Another feature is the direction. The length of the vector can be calculated by performing the Pythagorean theorem. Here we are in 2D, the same concept apply in 3D. For simplification, we will only talk about it in 2D here. So when we say vector 3, 4, for simplicity in mathematics and in linear algebra, we usually represent that vector as 2 points. That's the first point as 0, 0, and the second point or the end point as 3, 4. But is this the only 3, 4 vector? No. If you look at the image to the right, can you tell me, Dr. Salim, are these all the same vectors?
No.
They are the same vectors.
Yeah, they
Okay.
have.
Well, maybe I asked the wrong question. My bad. Do these vectors have the same direction and have the same
Yes.
length?
Yes.
Exactly. They do because they have the same length, and the direction means the angle it makes with the x-axis. So the idea here is that the most important features that we care about a vector is the direction and also the length of it.
Mhm.
And again, for simplicity, when you in textbooks, actually, when you see a vector, they need to draw it. So they probably select a starting point, and that's usually the origin, and the end point is a 3, 4. Is it good so far?
Good.
Now, before we proceed, we need to have a conversation, an honest, transparent, and straightforward conversation with our dear host, Dr. Salim. Are you ready, Dr. Salim, for the advice?
Ready.
Okay, so not everyone will understand, will think the same way that you do. And in fact, they will not see the things the way that you see them. They never did, they never do, and they never will, if you will. What does that mean? That means what Dr. Salim might see this picture as a hamburger with very tempting cheese and look at the green lettuce. Someone else might see this as a vector. He will automatically in his mind make a vector and imagine calories, saturated fat, trans fat, total fat, price, and carbs, and then put these numeric attributes of the burger uh,
Mm.
in a vector. Again, what might Dr. Salim see this as a Mercedes? I'm pretty sure Dr. Salim is a good driver because we've hanged a lot and drove a lot together. So what might Dr. Salim see this as a car? Someone might see this as a vector. Automatically, his mind will imagine a vector has an armature, has an engine size, and curb weight, and power horse.
That
Our
someone that someone is the computer or you.
Exactly. The computer also, yeah, exactly. Yeah, exactly. Yes, yes. This is how we feed the computer. We cannot tell the computer a car. We need some numerical form that the computer understand. And that paves the way to how we represent the world as a vector. And someone with, let's say for us, the normal people, if I want to go to visit Dr. Salim in Buffalo, we both met in Binghamton University, by the way. And then Dr. Salim moved to Buffalo 3 hours away. When I wanted to visit Dr. Salim, I enter on the GPS his address and it shows me the best route. Somebody might represent Binghamton as a vector and might represent Buffalo as a vector and then look at the sign of the angle between these two vectors. So here, that's a important concept is that a measure of how two vectors are close or far to each other is the angle between them. That's called the cosine similarity. Similar thing, another example for Portland, Oregon, just to reiterate the concept. We can represent Salem as a vector, Portland as a vector, and we measure the angle between them. Let me give a little bit more features, a little bit more details here. Why this analogy is so important. In recommender systems, for example, you have a product, right? And you have another product, and they actually represent each product as a vector. And once you represent two products as a vector, for example, one as Binghamton and one as Portland, you can measure the angle between them. And you can say these products are similar. And if a customer bought the first product, I can recommend him to buy the second product. So that is one of the core concepts, or one of the most important um, feature of mathematics is that once you represent daily object in mathematics, you you utilize and you make use of the magic of mathematics and the rules to draw conclusions and understand more about your daily objects. Once you are able to represent them in a mathematical form, like in linear algebra or vectors or mathematical model, you will be able to use the huge power of mathematics to draw conclusions and make more understanding about the data. So somebody, again, or Dr. Salim might normally see people in the streets. Someone else, like the computer, might see everybody as a vector. Even people walking in the street, it sees them as vectors. And this takes us to the concept of word as a vector. So what is better, to represent a word just as a sequence of characters or character codes, or represent them this way? Here to the left, we have the vector represents positivity. It have different features. I mean, it doesn't have to be that way, but this is just an intuition to help us understand how representing a word as a vector can give more meaning to it in the eyes of our dear computer. So we have positivity, we have violence. Is the word violent? Is that word optimistic? Is that word romantic? How common is that word? The more value, for example, in the first row or the first element, the more positive that word is. So even for a specific word, we can make features and give scores to these features. This is the type of intuition about representing a word as a vector. And we will talk more about this in the next lecture and the next presentation. Now, what is a word? That might seem a philosophical question, but what is a word? This is not an official definition or a dictionary definition of what's a word, but based on our understanding of the language, a word represents a concept or an object or an action, right? Um, the question that comes now is, can we break this word into smaller units that also convey a meaning? For example, we have disagree, disengage, disproportional. You see, we have highlighted those in red. This means not. For example, disagree, I do not agree. Disengage, I do not engage. Disproportional means not proportional. So we can break a word into sub-words. Now, let's see an example. Let's get more intuition about what a subword is. A common example is the prefixes and suffixes. Malfunction, it's not functioning correctly. Misspelled correctly. The MIS at the beginning of the word. And it's not only about the prefixes and suffixes. For example, when I was a kid, I remember from my English class, people were bragging about who knows the longest English word, and this is just one of them, anti-disestablishmentarianism. So it's not about prefixes and suffixes. Some of these subword can be also in the middle of the word. And we can talk a little more examples like theology, theocracy, implode, explode. You can think as implode, collapsing forward, explode, collapsing onward. So it can some. This is again an intuition that some part of the word that's not a word by itself can convey a meaning. So how do we know these subparts of the word that can convey a meaning? Frequency is a clue. So if we look at a subpart of the word that appears over and over in other words, then that's a clue that this could be a token or a unit that is important. Overlook, overdo, overthink, and overlook. Over here is part of all of these words. And again, it's not about prefix, suffix. A character itself can be a token or a single letter, but this is the idea behind the tokenization. It can be a subword that has a meaning, but a word by itself. So this is where the tokenizer kicks in. A tokenizer looks at a large corpus of data, textbooks, articles, whatever, songs, and then it figures out the tokens. So what tokenizer does is that it has two inputs, a large corpus of data and also the number of target tokens. It starts with basic tokens and then keeps figuring out more and more tokens. We will explain this in detail in the next few slides. So for example, the GP2 tokenizer receives, according to their documentation, receives 40 gigabytes of text and the target is 51,000 tokens and it produces 50,000 tokens. And there are multiple actually tokenizers, example word piece, sentence piece, and the one we will be covering today is byte pair encoding. So let's see how byte pair encoding works. The idea is very simple. The first that you have a corpus of data, and again, the corpus of data is a huge collection of articles, books, text, songs, whatever you can imagine. And then you have the alphabet or the set of the characters, and these are from A to Z. And you imagine that these are the tokens that you start with. And after that, you make merges. You merge every character or every other character. A, B, for example, is a possible token or a prospective token. BC, CD, ZN. And then it looks in the whole corpus which of these merges is the most frequent. And it selects the most frequent one and it's added to its set of tokens. That's in the second iteration. And it does the same in the third iteration, fourth iteration. And at each iteration, it adds one more token until it reaches the target number of tokens. So that's how it basically works. And it's very simple. It's really very simple. And we can even easily look at other algorithms and understand how they work. Dr. Salem, I want to check if you have any
Can you go
suggestions.
back to the previous slide?
Yes, this one.
So this all example of tokenizers. Can you repeat the tokenizers a little bit in the previous slide? Because it's
Yeah, so there are different tokenizers that work a little bit differently. One of these is a word piece, sentence piece, tick token. So here we were just mentioning them to be aware that there are different tokenizer and a little bit different in the way they work. And the one we talked about and explained is the byte pair encoding.
nice. Go to the previous slide, the one
Yep.
before this one.
This one, yes.
Okay, so there is a token. Go to the ChatGPT or any generative AI. What is the 51K means?
Oh yeah, that's a good question. So this is the number of target tokens that the ChatGPT will produce.
I see.
So if you look here again, we start with the basic tokens, which let's say the number of alphabets or characters in the English language, and each iteration we add a new token. Until so the tokenization process receives two inputs: the large corpus of text that it will build the tokens from, and a target number of tokens or the vocabulary. Right?
Right.
And if we are ready to move to the next slide,
Yes, go
let
ahead.
me
Go
know.
ahead. Go ahead.
Or if you have additions.
No problem.
So this is an example from the Transformers API, basically just a Python notebook where I give it a text and see what tokens will be produced. So I'm saying pre-calculus is not really as difficult. So if you look at it, recognize that pre. So this is an actual tokenizer called BERT-based uncased. And if you look at here, you see that pre is recognized as its own token. Well, not all of the tokens produced by the tokenizer will be understood, but this is what we've alluded to earlier, is that a prefix and suffix could be recognized as tokens, and they help us that some of the tokens, or maybe majority of the tokens, maybe convey meaning that we necessarily didn't understand. And if you were preparing, for example, we international students, we prepare for GRE exam, and we have to study thousands of words. to be able to pass the exam. And then we were able to identify a lot of these tokens as we like a lot of these patterns in words. Another example, there is a lot of misconceptions about the AI, and there is the word miss, right? Here it was recognized as a token, like misprediction, misconception, misbehavior. There is a lot of examples on these words. So miss is being recognized as a token. So honestly, I was very excited that to see that it really recognizes some prefixes when I was preparing for the lecture. And again, not all of the tokens will understand the idea behind them, but again, intuition is very important. Having an idea of how it works actually makes us even we can build it ourselves. You don't need to look at a code. This actually you don't need to read a book of how it works. Once you understand the concept, you can understand the algorithm better than reading about the algorithm itself. Right? And last but not least is what we've mentioned before is that why do we need tokens? Is that when we give a text to the chat GPT or to the large language models, we need to tokenize them first, like we've done here. And you probably, if you look at any sample machine learning code, you will see this quite often. They always tokenize the words. They use a pre-trained tokenizer, and then these tokens are fed into the large language models. So what we hope in the list lecture is we will be able to understand or explain well how each of these tokens is translated or transformed into a vector. So by now we have covered the concepts that we wanted to cover. And if there is any slide Dr. Salem, you want us to go back to or illustrate further on any question, anything that you might have, that will definitely make us understand more things and enrich the conversation.
Thank you for this good presentation. I really appreciate it. And we are looking forward to the next. I don't know, can you give us the hint what you're gonna present next?
We will probably talk about the where to vector algorithm, and specifically, we will talk about the log function and the softmax function. It's going to be a little bit mathematically involved, but not too much, not that big math. And we will go back to the concept of the neural networks. Like we will use a neural network, and we also will talk a little bit about the rate of change that we promised in the first presentation that we will not mention that often.
Thank you so much, Dr. Khaled. I really appreciate it.
Thank you, Dr. Salim. Thank you so much.
Thank you.